speaker. How do you pronounce your first name?
Gergely.
Gergely. Gergely Tish from
Yes,
Budapest.
Yes.
On
Exactly.
the Fuglede Conjecture, please.
Yes, thank you very much. So this is a continuation of a kind of continuation of the talk of Gábor Somlai from yesterday. Today, I would like to talk about the Fuglede's conjecture on the direct product of finite abelian groups. I give an overview of the known results and pose several questions. So this is the plan, and I start. So let's start. So G be a locally compact abelian group, and G hat denotes the dual of G, and mu denotes the Haar measure on G, and let S be a subset with positive and finite Haar measure. We have two main cases. One of them is the Euclidean space where mu is the Lebesgue measure, and the other one is either Z to the D or a finite abelian group when mu is the counting measure. So a set lambda, so now I fix S, and a set lambda is called the spectrum of S if the characters, the elements of lambda, gives an orthogonal basis of L to S. If there exists such a set, then S is called the spectral set. And similarly, S is called the tile of the group T if there exists a set T such that up to a set of measure 0, every element of G can be uniquely written of the form S plus T, where small s is from the large set, so the set S and T is from the set T. This we denote by S plus T is equal to G, and T is called the tiling partner of S, or sometimes I call it tiling complement. And Fuglede's conjecture states the following: the spectral sets and tiles coincide in R to the N, and as Gábor mentioned yesterday, this conjecture fails. I will talk about it a little bit more than yesterday. So connected to the conjecture, Fuglede proved that if S is a tile whose tiling partner is a lattice, then S is spectral. And on the other hand, if S is spectral with a spectrum which is a lattice, then S tiles R to the N. So here his conjecture is true in this sense. So after some remarkable positive results in one dimension and in the cyclic group case, which are closely connected as we get to know yesterday, Terence now disproved the conjecture by showing that Fuglede's conjecture is not true in R to the N for if N is greater or equal to 5. In particular, he showed that there exists a spectral set in R to the 5 that does not tile. So the sketch of the proof is something like this. Find a counterexample if in a finite abelian group with N generators, extend it periodically to Z to the N, and blow up the points to unique cubes, which gives a counterexample in R to the N. So this type of idea is fundamental in all counterexamples. So therefore, from now on, the counterexamples were searched in a finite in a product of finite abelian groups. So in particular, in this theorem, it is enough to show, for this counterexample, it is enough to show the following: there exists a set S in Z3 to the 5 which is spectral but does not tile. So this set is can be taken as the elements of the standard basis of Z3 to the 6. So this set has size 6, so it cannot tile this group. On the other hand, S is spectral. To see this, we take the following Hadamard matrix, where omega is the third root of unity. So then we can choose lambda to be the elements now on the group, not the dual, such that these sequences e to the pi and the scalar product ej xi k over 3, this sequence is exactly the case rows of the Hadamard matrix. So for ck, the case rows. For instance, we can easily calculate such size. So xi1 is this one, xi2 is the second is 0, 0, 1, 1, 2, 2. So we can just see the exponents and we can easily calculate it. So we have a spectral set which does not tile in Z3 to the 6. Now we push down the dimension by 1, take a translate of lambda by the translate of S by taking S minus E1. So it's 0, and E2 minus E1 and so on. So this is in a finite dimensional hyperplane defined by this equation. And similarly, lambda can be seen as a subset of gamma, which means that also the spectral set, also the spectrum lives in gamma, which is isomorphic to Z3 to the 5. So we get the result. Yes. So the next improvement is by Matolci, who instead of the Hadamard matrix, he see the log Hadamard matrix. So for the original Hadamard matrix that we take previously, we can take the log Hadamard matrix K, which is defined by this equation, where in the exponents we can see the entries of K. So then K looks like this. If you can see, this is exactly the elements of so the list of psi K's. If we go back, here is psi1, psi2, and we can see exactly these elements right here. The rank of K is 4 mod 3. This has an important role because then K can be written as a product of two matrices, mod 3, which is L is a 6 times 4 matrix and S is a 4 times 6 matrix. Why it is useful? Because if we take the columns of S, it is a spectral set of size 6 is Z3 to the 4. And this automatically, as previously, implies an example in R to the 4. This was improved by Farkas, Matolci, and Mora, who showed that for Z24 to the 5th, this type of construction also works. So they produce a counterexample in R to the 3. So they show the spectral set, which is not a tile. Now we are looking for tiles which are not spectral. And the investigation of this type of problems started by Kouluntzakis and Matolci in 2006, who realized that it has a close connection with the following conjecture. So the universal set conjecture is the following. If we have a set S, which ties a group with tiling partner T1, Tn, then they are spectral and they have a common spectrum. This conjecture was posed by Lagarius and Wang, who proved also the following theorem, which is the key, which was the key for Kouluntzakis and Matolci as well. If a set A is a common spectrum for T1, Tn, then A ties the dual group with any spectrum of S. So since there is a spectral set now instead of G, we take it on G hat, that is not a tile, its spectrum is a good candidate for such an S. So the problem is that the previous construction is based on some divisibility condition for the size of the set, which would fail also for S itself. So we want that S is a tile, so this divisibility condition cannot fail. So therefore, instead of Z3 to the 4, Z3 to the 5, we worked on Z6 to the 5. And we take this set 0 and the elements of the standard basis in Z6 to the 5. Then S is tile in Z6 to the 5 and also spectral with the following spectrum. However, L is not a tile. Why? Because L is in a subgroup which is Z3 to the 5. So we have a 6-element subgroup of Z3 to the 5. It cannot tile, and it implies that it cannot tile the whole group as well. So and therefore, the tiling partner of S has no common spectrum. So this shows that the universal spectral set conjecture fails for Z6 to the 5. And the next step to get a tile which is not spectral is I call it gluing method, which I try to summarize in the following proposition formalized by Farkas, Matolci, and Mora. The universal spectral set conjecture is true for every finite Abelian group generated by D elements, if and only if every tile is spectral for every Abelian group generated by D elements. So one direction is straightforward because this is a stronger state. The first one is stronger statement, but on the other side, we can do the following procedure. So if a tiling partner of a tile has no common spectrum in this product of cyclic groups, then for a large enough P, we can list all the tiling partners, some maybe repeatedly, which altogether ties this group. this larger group. So we take the times p as times zp at the end. But as p is taken to be very large and co-prime to the ni's, this can be taken as a group of D generator, and this set which is a tile has no spectrum. This is for sure a statement that we have to prove, but it is true. So in this case, for Z6 to the 5, P equals 17 is good. And this shows that Zp to the 5th times Z17 has no spectral tile. So R to the 5 has a non-spectral tile. Further development was initiated by Farkas and Révész, who proved that the same result for Z6 to the 4, that universal spectral conjecture fails. So in R to the 4, tile spectral direction fails. And later, Farkas, Matolcsi, and Mora shows similar consequences for Z24 to the 5th, and hence for R to the 5, R cubed. So summarizing the results, both direction of the conjecture fails in R to the 4, R to the n, if n is greater or equal 3. So, and the main question of this area can be formalized as follows: does Fuglede's conjecture hold in R or in R square? In R square, as we see, it would be enough to find the logodomard matrix of rank 2 mod n. Unfortunately, we don't know that, but our main question in the rest of the talk is the following: what are the finite abelian groups where Fuglede's conjecture holds? This is a very general question, and I try to show some special classes which are well understood. Fuglede's conjecture on direct products of elementary P groups is the first class of this. For odd prime P, Fuglede's conjecture holds in Zp square, so in Zp times Zp. This is a result of Iosevich, Mayeli, and Pakianathan, and does not hold in Z3 to the 5. This is a result from Tau. This is the original what we talked about. This was improved for Zp to the 5, to Zp to the 5, where it does not hold. And in some cases for Zp to the 4, later this was also improved by Zp to the 4 by Ferguson and Sortanapan, and simultaneously by Sam Matthews. For P equal to 2, the question is slightly different. So Fuglede's conjecture does not hold in Z2 to the D if D is greater or equal to 11. This was also in the same paper, proved in the same paper by Tau, and later it was improved by these guys Ferguson and Sotanapan, that it was improved to D greater or equal 10. And they also showed that it holds in Z2 to the D if D is smaller or equal 6. One comment is that the counterexamples are based on the existence of the corresponding logodomard matrix, and this proves the spectral tile direction, always the spectral tile direction only. We can understand why, because the other direction we have to use the universal spectral set conjecture and then go back to the original problem. But there we should add some additional ZP factor. Okay, so this motivates the following question, the following conjecture from Roxishi. So every tile is spectral in this in this abelian group, which is a product of P groups, where the coefficients are in positive integers. In particular, is it true that every tile is spectral in ZP to the D? Some other open questions, I just summarized the previous results, what is open now. So is Fuglede's conjecture true in Z2 to the D if D is between 7 and 9, and ZP to the 3 for odd P, odd prime P? We have some partial results in this case, so the answer is yes for P if P is smaller than equal 5, and later it was improved to P is smaller or equal 7. This is a result of Fallon, Mayeli, and Villano. About ZP to the cube, it is a very interesting and it seems a very hard question as well to prove that. I try to summarize what we know now. So we know that every tile is spectral in ZP cube. This follows from the following statement. Every tile of size P is spectral in ZP to the n, and every tile of size P to the n minus 1 is spectral in ZP to the n. So for instance, this implies immediately that every tile is spectral in ZP cube. But for instance, it implies a question: is it true that every tile of size P square is spectral in ZP to the 4? In the spectral tile direction in ZP to the cube, we have the following knowledge. So it is known that every spectral set S is a tile if the size of S is either 1, P square, or P cube. We also know that if the size of S is greater than P square and spectral, then it has to be the whole group. If P is smaller than 7, smaller or equal to 7, then every spectral tile is a tile. We talked about it. So to prove Fuglede's conjecture for ZP to the cube, it is enough to show that to answer the following question: does there exist spectral sets of size P of size S, which is strictly between P and P square in ZP to the cube? This would imply, if the answer is yes, this immediately imply a counterexample for the Fuglede's conjecture. I have to mention that this S, if it is spectral and non-trivial, so not only one element is in S, then the size of S is automatically divisible by P. So here in this inequality, we should think on the multiples of P as the size of S. And for the rest of my talk, I would like to talk a bit about mixed direct products, which is usually can be imagined as as a product of two cyclic groups where the order of the groups are different. So the Fuglede's conjecture is true in ZP square times ZP. This is a result of Ruxi-Shi, and this was improved by Tao Zhang last year, who showed that ZP to the n times ZP, the Fuglede's conjecture also holds. Both authors mentioned that these results can only used when the second part is just a ZP, not a ZP to the n factor. So it is some improvement that we proved recently with Gábor Somlai, that the tile spectral direction holds in ZP square times ZP square. And the question generally is that does Fuglede's conjecture hold the ZP to the n times ZP to the n? It automatically implies that it holds for ZP to the n times ZP to the m for a different NMN. But telling the truth, this idea, still this proposition, use some extremality of the tile in ZP square times ZP square, which is not necessarily the case in the higher dimension, for higher n. The other mixed product that we studied is Fuglede's conjecture in ZP square times ZQ and ZP square times ZQ square. So the first is a joint work with Gábor Somlai, and the second one is a joint work with him and with Tom Fallon. So here we assume that P and Q are distinct primes, and we show that Fuglede's conjecture is true in these cases. And just a few words about the proof is that the spectral tile direction is based on the equidistributivity property of spectral sets in cyclic groups that are naturally embedded in ZP square times ZQ and ZP square times ZQ square. So this sentence sounds very, very simple, but in both cases it is a case-by-case argument. But there is one case where we have to understand very deeply the structure, and this case is very hard to handle. The dispectral direction, as usual, slightly easier, and it is based on the following observation. So if we have a tiling A plus B is equal to G, where the intersection of these two sets is only the 0, then we can write the following sequence of equivalencies. So A plus B is equal to G. It is equivalent to that the characteristic function of A convolution with the characteristic function of B gives the characteristic function of G. So in a Fourier space, it means that the Fourier transform of the characteristic function of A times the Fourier transform of the characteristic function of B is equal to the size of G times the trivial representation. So this means that for every chi, which is not the trivial representation, chi A, which means that the sum of all elements of A, chi A, where A is from the set A, and the same definition for chi B. So every character vanishes on A or in B. This is a very strong condition, and this helps a lot. And after again some precise analysis gives that the high spectral direction holds. So all in all, that's what I would like to tell. So thank you for your attention, and here are the references that I used. Thank you very much.
Thank you very much. Are there questions for our speaker? Check the chat. If not, thank you again. Our next talk is in 9 minutes.